Hello everybody, welcome to Lab 5, the Falling Slinky. This is the last lab for Physics 2211 at Georgia Tech. So today what we did was examine a video of a spring at static equilibrium and then observed its motion as it was dropped to the ground. So the system for this experiment was a spring and then the surroundings was everything else. The purpose of this lab is to analyze the computational model and an observed model of a spring that is dropped from rest. And we did this in the y direction only. So to do this, we make a tracker model of the observed video, and then we plot the position versus time graph in the y direction for position. And then we will construct a computational model on GlowScript, and then basically do the same thing, make another graph of the position in the y direction versus time, and then we will compare the two graphs and see how they have similarities and differences. So the important concepts for this experiment is Newton's second law, which states that F net is equal to the change in momentum over change in time. And then in addition, we have the position and velocity update formulas to basically predict our motion and the change in position for our computational model. So here is the observed motion video.
All right.
3, 2, 1, drop.
Wow, did you see that? All right.
And then here are the initial conditions, data, and tracker video for that video. So our initial conditions, I set everything to 0, so time equals 0 seconds, y position equals 0 seconds, and then the velocity in the y direction was 0 meters per second, and then once that begins it will be in the negative y hat direction. So also we have our corresponding data values, and then there is a position versus time graph, and then on the right here we have the tracker video, basically just having the motion tracked until it hits the ground. So here is our computational model. The initial conditions for this one was that the initial position and initial velocity were all 0, and then there is the mass of the, it says ball, but it's a slinky, and then here is the computational model. Okay, very nice. So here was the associated code for that model. Basically, I just put all the initial conditions in and created a graph for the data to be inputted into. And then we have iteration here just to, and basically the iteration is just finding the ball's or not the ball, it says ball, but it's a slinky. The slinky's velocity and position at each delta t, and I set delta t to be 0.02, so at each time step we just have a different position and different velocity. Here is the associated data points for the time versus position, and then also here is it graphed. So next thing I did was I put the computational model and observed model all in one graph. So here's that. The red line here is the computational model and the blue line is the observed model. As you can see, they differ quite a bit. The computational model looks a lot smoother, and also the observed model has greater delta y, and I think this is due to error, which I will talk about in a second. But moving on, I have a relevant question. So does the bottom of our model of a slinky stay stationary? And the answer is yes, it does for a little while due to tension force, probably the spring force canceling out the gravitational pull, making the motion equal to 0. So my conclusions here were that Newton's second laws were met, as we can see in the videos, and the computational model and observed model differ a lot in consistency, and that could be due to a lot of inaccuracies on my part or drag force, but also me placing the tracker on the mass, and that could have accounted for these differences. So my what if question was, what if we also accounted for the mass at the end of the slinky? How would this change our data? And basically, if we did this, this would just increase the forces acting on the system. Then we would have to account for extra gravitational pull, and therefore the velocity will probably increase at an increasing rate. So thank you so much for watching, and I hope you have a great